friends, welcome back. Now let's look into another interesting topic in the memory management, which we call virtual memory management. So what are the virtual memory is? Virtual memory is a memory management technique where the operating system makes the computer appear to have more memory than it physically has. That's RAM. So we are able to use much bigger process in a limited space. So though we have a limited space, limited memory physically available, but if we can make a bigger process to run, so it appears as if we have sufficient memory to fit all the process onto the memory, and that is the concept of virtual memory. So here what actually happens is we have reserved some space in the main memory for any process, and the amount of the memory reserved for that process is fixed for a process. And if our process in reality has a bigger size, then a part of that process will be taken onto the main memory. Rest all will stay back in the secondary memory or the hard disk or SSD. So in all, what happens is a bigger process or a process requiring a large amount of memory can work even with a small RAM space available, so that whatever available RAM space is there, only that part of the code, that part of the process is on the memory. Rest all we keep it in the back end, and that way it appears as if we have full memory available for our process. So the program see a large continuous block of memory, which we call a virtual address space, but behind the scene only a part of it are actually loaded onto the physical RAM. Rest all are on the secondary memory. So here it gives a straight answer for our explanation here, whatever we are trying to say. So we are talking about our process, which has got say 5 pages, A, B, C, D and E, and out of these 5 pages our process got memory sufficient to fill only 3 pages, and 3 pages like A here, B here and C here are put on the memory wherever it is allocated. So A, B and C are on the main memory, whereas D and E, which were a part of a process but they don't find space in the main memory, so the pages D and E are there and the back end in the secondary memory. So anytime if D is required, then one of the 3 A, B or C will be moved out back to the secondary memory and D will be replacing that place. So that way anytime we can make sure that 3 pages are on the physical memory, and because only 3 pages are allocated for this particular process, and this particular process do have 5 pages long, so we can't have all 5 pages put on the main memory, so we put any 3 pages which are required at this instant, and other 2 will be always residing on the secondary memory. So that way we anytime A, B, C, D, E, one of the 3 out of these 5 will be there in the main memory, other 2 will be on the secondary memory, and it appears as if all A, B, C and D and E are running one after other in some order as per the process, and all are running. So for the user it appears as if A, B, C, D, E, all 5 pages are actually accommodated on the physical memory, but actually there are only 3 got the place, other 2 are in the secondary memory. So that is the logic of virtual memory in this case. So why do we require virtual memory? So first thing is of course want to run large programs. Then if we want to run programs which are of bigger size, then it may not be always possible to have sufficient space in the main memory. Therefore this virtual concept will definitely help us to run any size programs with a given limited memory, and this we can make by swapping parts in and out of the main memory, back and forth from the secondary memory and primary memory, just swapping them between primary and secondary any pages, and making sure that the allotted pages are efficiently used for any size of the program. When we are working on multi-programming or multiple processes, then they can run together, each thinking that the big private memory is with it, even though the RAM is limited. So we have a limited RAM, and that limited RAM, we divide that into different portions, and a small portion of each will be given to one program or one process. So at any given time, with the available small memory, a more number of processes are accommodated simultaneously. So in parallel, it looks like all the processes are running. So they are not getting enough space. Each process is not getting enough space. Therefore, whatever space it has got, it is going to use that. Rest of the part will be there in the back end. So swapping in and out these pages from main memory back to secondary, secondary to main, this is done at every process level, and at the end it looks like each process has got sufficient RAM, though in reality the RAM is of limited size. So that virtual memory concept gives an illusion to every user that each user has his or her own independent RAM sufficient to fill the whole process onto the RAM, and that mileage is created through this virtual concept. Then other issue is isolation and the protection. So each process gets its own virtual address space, so preventing one program from crashing or accessing others' data and all that. So that's another important issue, that we don't want one process to interfere with other process. So through this virtual memories, we can make sure that each process has its own virtual space. So and that way we can keep the processes isolate and protect them from one another. And at the end, you can say that efficient memory utilization is there, because any part of the any process, if you take whatever size the process is, any given time one part of the code will be running. So it's almost useless to have the whole process put onto the main memory, because the whole process will not be running any given time. Only one code or one instruction is being run at any given time, and whichever page that instruction is containing, if that one page was there on the main memory, that is sufficient to execute the process. So we don't require whole process to be dumped onto the main memory before executing it. So whichever part we are executing currently, only that part is sufficient. So we don't have to waste our memory. So any given time, one process needs one page to be there on the main memory, whichever it is currently executing. So if we have some n pages in our main memory, then in the best way we can accommodate n individual processes, giving each process one page, because any given time only one page will be executing. So that way we can ensure that best utilization of the memory can be taken up through this virtual memory concept, and that makes our programming model simpler. So now we can write as if there is unlimited memory without worrying about the physical memory limit. So when I am writing a program in a high level language, I may be using C, C++ or C hash, or maybe Python, Java, anything. But when I am writing a program, I will never bother about what the hardware I have at the base level. I don't mind what processor I'm working on. I don't mind how much RAM do I have. I never bother how much of that RAM is made available to my process by the operating system, so that all are none of my botherations. My botheration is to write the code to solve my problem. It may take any number of pages, that doesn't make any difference to me. It does make difference to the operating system. It's all the problem challenge for the operating system to make sure that my process runs smoothly and gets me satisfactory results to me. That's what the operating system is supposed to do. So we don't have to worry much while writing a code. So that makes the user's headache to the least possible level. So it creates the simplest possible programming model. So we don't have to worry much about what exactly is there in the physical memory and all that. So if we were working at the hardware level, like if I am working on 8085 machine, then we were in reality working on the actual physical memory address space and all that. So I have to know at what location my program is being written. So I need to know what is the size of the RAM our system is having, and I don't have any access to write my code larger than that particular RAM available on the system. But now we are working with the operating system, and these all headaches are taken care by the operating system through virtual memory concept. So I don't have to worry anymore about size of my program, where it is going to be pushed onto the main memory, and how it is running, and how this swapping is done in and out. None of my problems. So the user don't have to worry at all. It's the operating system's headache. So let the operating system take care of that. So that's why we enjoy life, because of this virtual memory being implemented at the operating system level. So for example, if you are talking about a memory which is having 4 GB RAM, but if I want to run 8 GB program, then we can make sure that 8 GB RAM is used for storing the that this 4 GB RAM will be used to store part of the 8 GB program. So what we can do, first part of the 4 GB put on the RAM, let the second part of the 4 GB be on the secondary memory or hard disk. When we require second part, then we swap first part, get back to the main memory, secondary memory, second part get to the main memory, and that way whichever part, first part, second part is to be run, that comes onto the main memory, the other one goes back to the secondary memory, and this swapping is done whenever required. And that way, even though our RAM is of 4 GB, we can run 8 GB, 10 GB, 100 GB, whatever size you tell, doesn't make difference. Yes, we can run through the concept of virtual memory. So whenever a program tries to access something which is not there on the RAM, then the operating system will swap the pages between the RAM and the disk. So this way we can just show that there are the virtual memory, so many pages are there, and this memory mapping is done. So that actually talks about which page of our process is mapped to which physical frame, and then we have a secondary memory here. So that is the primary memory, this is secondary memory. So we want pages. So these are the pages of our process. So the virtual memory of our process, which is containing some n number of pages, and out of this, whichever pages are there on the main memory, yes, it is still, that is information is available with the memory map, and we have some pages on the main memory, and rest of the pages are there on the secondary memory. And when our process is running, then the pages which are there on the main memory will be running, and when that part work is over, then we have to get another page from the secondary memory, which we call swapping in. But before swapping in, we should release that page. So that page, whatever was there, should be swapped out, and a new page is swapped in. So this swapping in and out is done between the main memory and the secondary memory, and that gives an illusion that we do have infinitely large physical memory with us. So any time when you say process, then we do have a virtual space for every process. So this virtual space for a process will consist of some place to store the code, some place to store the data, some place to store the heap, some place to store the stack, and so on. So in the virtual language, we show this whole thing at one place, but it's not necessary that everything gets a place in the physical memory. So some part of the code may be available on the physical memory. The rest of that has to be on the secondary memory. Some part of the data may be getting a chance to be on the main memory, rest has to be on the secondary memory. Some part of the heap may get a place in the main memory, rest will be there in the back end. In the same way, some part will be getting a place in the main memory, rest should be residing on the secondary memory. And whenever need arises, then we need to swap in, swap out the pages between the main and secondary memory. But logically, our process looks like this, but in reality, our process is totally different. Some pages of code, some pages of data, some pages of heap, some pages of the stack get chance to be on the main memory. Rest of them will be in the secondary memory. Not necessarily that they are in a contiguous positions. They can be spread out anywhere in the main memory. They can be spread out anywhere in the secondary memory. That is not the matter here. What matters here is logically it looks like everything is intact, though they are scattered out, some in the main memory, some in the secondary memory. But for the user, it looks like everything is at one place, fully available, intact, and all that. So that's the advantage of working with the shared memory. Then when we were working with multiple processes, then we can have shared libraries. So these shared libraries also we can have through the virtual memory. So we say that our process will consist of one shared library, and another process also consists of another shared library. That is what logically we are saying, that we have a shared library here, we do have another shared library here, but in reality, shared pages are there on the main memory, and these shared pages are utilized by this process as well as this process as and when need arises. So through this, even with one copy of the library which is shared among multiple processes, each process thinks that that whole library is available exclusively for itself. So each process will have illusion that this particular library is available only with it, though among all n processes which are using that particular library, there is only one copy of that, and that one copy may not be totally available on the main memory. If that library is big enough, and if sufficient pages are not available on the main memory, then again, as we said, some pages of this library are put onto the main memory, other pages are well settled in the back end. So as and when need arises, these pages are also getting swapped between the main memory and the secondary memory. So through the virtual memory concept, we can create an illusion that simultaneously so many processes are running, and each process has its own memory as per its requirement. So it gives an illusion that we are working with an infinite physical memory, and that is possible only through the virtual memory. So that's some details about virtual memory. So if you find this of any use, please don't forget to like, share this video with your friends. Do comment your feelings and your what are the other needs, and please do subscribe to the channel. Thank you.